In this video, we're going to look at the derivatives of trig functions. And for those that haven't watched my videos or don't know, if you want to skip on to later things, look in the description below. There will be time codes throughout there that you can click on and skip past certain parts, because I will be proving all of the derivatives for the 6 basic trig functions. So first, let's list off the derivatives of the trig functions. The derivative of sine will equal cosine. The derivative of cosine will equal negative sine. And this is one of the patterns. So we have these sort of pairs of functions, and they sort of alternate, changing signs and switching the function. And so the derivative of tangent is secant squared. And once I know this, if I see, okay, cotangent, well, I switch the sign and switch the function, this derivative will be negative cosecant squared of x. And same thing here, so if I know the derivative of secant, which is secant x, tangent x, I can follow this pattern and say, okay, well, change the sign, change the functions, and I get negative cosecant x, cotangent x. And these should definitely be memorized. So what I'm going to do for the next 6 slides is prove all of these. The proof for sine is going to be a little bit involved, because I have to go all the way back to the limit of the difference quotient. But once I have sine, the rest fall into place very nicely, and I'll show you how that works. Again, if you don't need to see any of the proofs, feel free to skip to the example. If you need to see some of the proofs, I'm going to prove cosine based on sine, and I'll prove the rest of these based on sine and or cosine. So you probably would need to see the proof for the first 2 and whatever else you need to see to get to a proof that has everything in it. So let's dive right in. Derivative of sine of x equals cosine x. So for the proof, I'm going to start with the limit. Alright, actually, so I'm going to write this. I'm going to start with the left-hand side. The derivative with respect to x of sine of x will equal the limit as h approaches 0 of the difference quotient, which is going to be sine of x plus h minus sine of x all over h. Unfortunately, this doesn't work out as easily as the sum and difference, so f of x plus g of x, f of x minus g of x, and it's a little bit more annoying than the product and quotient rules. But it's not too hard if I recall the sign of a sum. So sine of x plus h is sine of x cosine h plus cosine x sine h. And I still have this minus sine x all over h, and I still have the limit. And now I can actually do some grouping. So when I look at this, all I really see is the fact that I have a sine of x here and a sine of x there. So I will group these terms together and have, so I'll have sine of x cosine of h minus sine of x all over h, and the rest I will leave separate, so plus cosine x sine h all over h, and this is all being done as the limit as h approaches 0. And what I can do is this. I can factor this sine of x, I can factor it all the way out. So sine of x, and what's left in this term is going to be the limit as h approaches 0 of cosine h minus 1 over h. Plus, I can factor out the cosine x here, and I'm left with the limit as h approaches 0 of sine h over h. And in here, so I want to get to cosine. I see a cosine here, and that is the cosine I want. All I need to realize is this right here, this term goes to 0. And if I actually were to graph this, let me think for a second here. Okay, this is going to end up around h equals 0 looking like this, and I can see from left and right I'm approaching 0. This right here approaches 1, and if I were to graph that, I would see from left and right it's approaching 1. And so I get sine of x times 0 plus cosine x times 1, which just equals cosine x. Alright, now for the rest of the proofs, they actually fall into place extremely easily. I might show a couple in a few ways, but here's the idea for this. So I'm going to start again from the left-hand side, the derivative with respect to x of cosine of x. But by the cofunction identity, I know that the cosine of x is just going to be sine of pi over 2 minus x. Now, if you don't know why, so because if I have a right triangle, and this angle is x, then this angle here is 90 degrees minus x, because they all have to add up to 180, and I already have this 90-degree angle, and 90 degrees is pi over 2 radians. So by putting in pi over 2 minus x, I actually switch from cosine to sine. And I can use that for any of these pairs, so cosine to sine, cotangent to tangent, cosecant to secant. But the nice thing here now is I can use chain rule here. The outer function is sine, so the derivative of sine is cosine. I leave the inner function unchanged. The inner function is pi over 2 minus x. The derivative of pi over 2 is 0. The derivative of negative x is negative 1. So this will equal negative cosine of pi over 2 minus x. And again, this is a cofunction identity. The cosine of pi over 2 minus x is just equal to the sine of x. And so I have negative sine x. Now that I have cosine and sine, I can go through and get the rest of the derivatives very easily, mostly using quotient rule. So in here, I'm going to, again, start with the left-hand side. So the derivative with respect to x of tangent x. And I realize that tangent is equal to sine over cosine, so the derivative with respect to x of the sine of x over cosine of x. And for this, I recall that the derivative with respect to x of some sort of f over g is g f prime minus f g prime over g squared. And so I take the bottom function and leave it unchanged, cosine of x, multiply it by the derivative of the top function, derivative of sine is cosine, minus the top function, which is sine, times the derivative of the bottom function, the derivative of cosine is negative sine, all over the bottom function squared, so cosine squared x. Multiplying this through, cosine x times cosine x is cosine squared x, minus sine x times negative sine x is plus sine squared x. Cosine squared plus sine squared equals 1 by our Pythagorean identity. And 1 over cosine squared x is the same thing as 1 over cosine x all squared, but 1 over cosine x is secant, so we have secant squared of x. Cotangent works almost the exact same way. So same idea, the derivative with respect to x of cotangent. And cotangent I know is cosine over sine. So the derivative with respect to x of cosine x divided by sine x. And I follow the quotient rule here, so I do the bottom function multiplied by the derivative of the top function, so times negative sine minus the top function cosine x times the derivative of the bottom function, which is cosine x, all divided by the bottom function squared, so sine squared x. And in this case, I get negative sine squared x minus cosine squared x all over sine squared x. And I can factor the negative out of here, and when I factor the negative out, I get sine squared plus cosine squared, which is 1. And just like before, 1 over sine squared is cosecant squared. And I still have the negative. And there we have that one. The derivative of secant. So this one I have two options. I'll actually show both. Again, if you don't need to see one or any of these, skip on down below. But I'm going to start with the left-hand side, so the derivative with respect to x of secant of x. And I recall that secant is 1 over cosine, so I do the derivative with respect to x of 1 over cosine of x. And I can do quotient rule here, but I have to be careful. So quotient rule says I do the bottom function, cosine of x, times the derivative of the top. Well, the derivative of 1 is 0, minus the top function, 1, times the derivative of the bottom. The derivative of cosine is negative sine, all over the bottom function squared, so cosine squared x. Well, cosine times 0 is 0. Negative 1 times negative sine is positive sine, so I have sine x over cosine squared x. And I can break this up as sine of x over one of the cosines times 1 over cosine. I guess I could have been smarter about this, but I wasn't. So I have to sort of reorder this to get the same thing that I had. So 1 over cosine of x is secant x. Sine of x over cosine x is tangent x. And there we have that proof. And the final proof, same thing. Oh wait, sorry, I said I'd do another way. Let me go back to that. Another option for this is the following. Instead of using quotient rule, I could use chain rule. So I start off the same thing, the derivative with respect to x. Let me change colors actually. Derivative with respect to x of secant x. And secant is 1 over cosine, so this is the same thing as the derivative with respect to x of cosine of x to the negative first. Now, I'm not writing this as cosine to the negative 1 of x because that is the same notation we generally use for the inverse function. But we want to use this as an exponent, not as an inverse function. So I can do chain rule. The outer function is this to the negative first power, so I have negative 1 times this to the negative second. And then the derivative of the inner function is negative sine. And the negatives make it positive. The negative exponent moves that to the bottom, and I do end up with sine of x over cosine squared x. And I'll put a little ellipsis, dot, dot, dot. That's where we were here. I can finish it off. Alright, back to this again. Derivative of cosecant of x. And again, I'm going to start from the left-hand side, the derivative with respect to x of cosecant of x. And I'll show it both ways again. I'll try to leave myself better room for it this time. So I know that cosecant is 1 over sine. So the derivative with respect to x of 1 over sine of x. Now I can use quotient rule. So the quotient rule says I will do the bottom function, sine of x, times the derivative of the top function, times 0, minus the top function, times the derivative of the bottom function, which is cosine of x, all over the bottom function squared. And in here, sine of x times 0 is 0. Negative 1 times cosine x is negative cosine of x. And I'll be smarter this time. So this can be written as negative, take that out, 1 over sine x times cosine x over sine x, which lends me to negative 1 over sine x is cosecant x, and cosine x over sine x is cotangent x. So that's the way to prove it using quotient rule. And similarly, I can use chain rule. So again, I'll start with left-hand side, the derivative with respect to x of cosecant x. And cosecant x is 1 over sine x, which is the same as sine of x, all to the negative first. Again, I'm not using sine to the negative first. That notation I generally reserve for inverse functions. The outer function is this to the negative first, so the derivative of that is negative 1 times this to the negative second. The derivative of the inner function is cosine. And from this, I still have the negative. I have cosine x in the numerator, and this negative exponent moves my sine squared to the denominator. And I can finish this off. So I would get negative, I'll split it up as 1 over sine of x times cosine over the other sine of x, which leaves us the same thing, negative cosecant x cotangent x. I almost forgot my QED. All right, now a little example. So the derivative with respect to t of secant cubed t squared plus 3t. So in here, it's just combining chain rule with our new trig derivatives. And recall, this is the same thing as the derivative with respect to t of the secant of t squared plus 3t, all cubed. The outer function is the cubed. So taking care of the outer function, I'll get the 3 out to the front, and I'll have this squared. So 3 times secant squared t squared plus 3t. So I've dealt with the outer function. Now I need to deal with the secant. The derivative of secant is secant tangent. So secant of the same input, t squared plus 3t, times the tangent of the same input, t squared plus 3t. And that's the secant taken care of. And then I need to take the derivative of the innermost function, which is t squared plus 3. And so the derivative of that is 2t plus 3. I don't think I said 3t. T squared plus 3t. And there's not much I can do here. I guess the only logical thing I can think of to do would be to maybe even distribute this 3 to the only algebraic factor we have. And so I would get 6t plus 9 times, I can multiply the secant squared times the secant because they have the same input. So I would have secant cubed t squared plus 3t times the tangent of t squared plus 3t. And that seems to be about as reduced as I can get it. All right, I hope this helped out. Feel free to comment down below if you have questions.